All right, we are now recording. Let's get from current slide. Okay, before we begin today, let me go over a little bit of housekeeping, what's going to happen between now and the end. Okay, first and foremost, how many have done the student course evaluations? Okay, still some who have not. Please do the student course evaluations. They really are on us pretty hard about getting those done. So please get the student course evaluations done. It's really useful information. Please get that done. Okay? Also, does anyone know what's happening next Tuesday? The election. Okay? If any of you are registered voters in the state of Alabama, and I know some of you are not, there's at least one Georgia boy in here and a few others that may not be. But any of you who are registered, please vote. Now, that probably creates sort of a problem for you. Number one, are you anywhere close to your polling station? Huh? If you are, you probably are going to have to vote on the way in, okay? Because I know I'm going to have to because I'm here till 8 o'clock. On Tuesday nights, the polls close at 7. So I've got to vote on my way in. Now, I've got a final 8 o'clock Tuesday morning, so I've already told that class I'm going to try my best to get here on time. But if there's a huge crowd there, which I'm hoping there is, I hope I'll be near the beginning of the crowd. And if there is, hopefully I'll get here on time. But if there's a huge crowd waiting and I'm not near the beginning, it may take a little while if they're slow getting the station set up. But usually they're pretty good about it. So please, if you are registered to vote in the state of Alabama, please vote. I don't know if you've still got time to do an absentee ballot or not. You may not. It's awfully close. But anyway, get into the habit of voting every time the polls are open. It's your right, your responsibility. Otherwise, you have no right to gripe, okay, because you deserve what you get. Okay, you probably don't deserve it, but you're going to get it anyway. Okay. Let's talk about the rest of it. We should finish Chapter 6 today, and that means we should have the lab on Chapter 6, the last lab on Chapter 6 today, okay? So that will wind up today in class until 5:45, and then in lab from 5:45 to 7:45, though it probably won't take us that long, okay? Next Tuesday is a regular class day. All right, and Jared is here, so we'll mark you present. So Tuesday, and if we finish a little early today, we'll go on and start Chapter 8. So we're going to finish Chapter 6, hopefully, and hopefully get started on 8 today. That means Tuesday we'll continue with Chapter 8 and get as far as we can, okay? Hopefully we'll get the lab done for the last lab for 6 done today. That means on Tuesday we'll probably have the lab for Chapter 8. Now the lab in Chapter 8 is a paper lab. There's nothing physical that we are going to be doing. You're just going to be doing it on paper. Okay? So that will be Tuesday. Now, that will wind us up for the term. Thursday of next week will then be your final exam technically, okay? Now, anytime after we finish whatever we cover in Chapter 8 and do the lab in Chapter 8, if any of you want to take that test in Chapter 8, okay, and by the way, since we'll finish Chapter 6 tonight, Thursday we'll have the test on Chapter 6. So Chapter 6 will be doing probably Chapter 8, and I doubt if we'll get enough done for the lab in Chapter 8, and then we'll do the test in Chapter 6, okay? And then on Tuesday, we'll finish Chapter 8, do the lab in Chapter 8, and once we're through with that, any of you who want to take the Chapter 8 test and the final exam, you can do so anytime after you turn in that last lab in Chapter 8 on Tuesday. So you can do it Tuesday night if you want to. You can do it any day, anytime Wednesday, or anytime Thursday. You have to have it done by Thursday, 3:15, come in. That's when we are normally scheduled. So if you want to wait until then, I will be here, and you can take your last test and final exam on Thursday at 3:15. But if you want to take it early, you can. Yes.
What's the final exam going to look like?
Say this.
What's the final exam going to look like?
It's going to look like the one that you had for your first course. It's going to be matching about 20 questions. I don't know if there's exactly 20. About 20 questions matching from all 6 chapters we will have covered. 1, 2, 3, 4, 6, and 8. Okay, so that will be it will be probably the easiest test you've had all term in this class anyway. Okay, and Andrew is here. All right, I think everybody's here who is accounted for now, I think. All right. So, does everybody understand? You certainly, the final exam is scheduled for not this coming Thursday, but the following Thursday, 3:15. But if you want to take it early, you certainly can. Actually, it's in 2 parts. There's a Chapter 8 test and then the comprehensive final. Yes?
If we take the test all on Tuesday, are we required to come to school on Thursday too?
You're not required. Once you take your final exam, you don't need to come back anymore. And that's why I'm doing it for you, in case I don't want you having to stay an extra 2 days if this is the only test you got waiting on. So I'll give it to you, but if you want to take that extra day to study, because we aren't going to probably finish Chapter 8 until Tuesday. So if you want a little time to absorb that and study it before you take your test, you can take it anytime Wednesday. Let me go through my schedule for next week. Well, this week and next week. My office hours tomorrow, Wednesday, are 3:15 to 5:15. And my office hours on Thursday, just like they were today, 1:15 to 3:15. On Friday, I'll be on the Birmingham campus, 7:45 until 11:45. Okay, that's regular week. Next week, finals week. Now, for full-term classes, it's strictly finals week. For you, mini-term classes, it's class week and finals week. Okay, so on Monday, I have what I'm giving a extra review session for my Math 100 class. So they will be in here from 8 till 9:50, close to 10 o'clock Monday morning. I will not be available for you to do anything then, okay, because I'll be in a review session with them. Okay, anytime after 10 o'clock on Monday, for the rest of the week, any of them can come in and take their final exam, which means I'm going to be really flexible. Okay, so let me explain what that means to you. My office is down at 265. I know several of you know where that is, and this classroom is up here at 255. If anyone comes in to do a makeup exam or something like that, I usually will try to find the closest classroom to my office so I can hear the phone ring, maybe be able to go back and forth and get materials if I need them. So I usually will give those makeup exams in a classroom between 265 and here. If all those rooms are occupied, we'll be in here because I'm the only one that teaches here except Dr. Bryant, and he doesn't teach except Monday, Wednesday afternoon when I'm not giving a test. Okay, so if you can't find me, look first in the office and then start looking in every classroom till you get to this one. I'll be in one of those. Okay, so that's Monday. Tuesday, I'm giving an exam in this room, 8 o'clock in the morning. It'll go till about 9:50. Okay, after that, I should be in the office or in some room in between there and here until our class at 3:15, and we're meeting as a class, finishing Chapter 8, doing the lab for Chapter 8, and then it's up to you whether you do your test for Chapter 8, your final, whatever you want to do, you can do it then. All right, then that's Tuesday. Wednesday, strictly final exams. I have no scheduled finals then, but I may be giving those makeup exams to either you or to that other class, and that will be anywhere between my office and here. All day Wednesday, 7:45 in the morning or 8 o'clock in the morning until 5:15 in the afternoon. Then Thursday, have nothing scheduled from 8 o'clock in the morning until 3:15. 3:15, any of you who haven't taken your test, the Chapter 8 test and the final, by then, that's when you need to be here to take your final exams, the last chapter test and the final exam. And then after that, Friday, I'll be on the Birmingham campus, 7:45 to 11:45. Any questions? All right. Now, let me go over a couple more things. I went through who was missing labs and tests, not who, but I am missing some. Also, the papers. Now, a couple came in today, but still, I have bunches of you who have not turned in your research paper. Yeah. That will be Tuesday. But please don't wait till then, okay? If you can get it to me any before Tuesday, it will be greatly appreciated, okay? But yeah, because that's the last day of class for this course, for this class, because it's a mini-term. The other classes is this week, but your class, because we do have class on Tuesday, you can turn it in on Tuesday without penalty. If it's after Tuesday, you start losing points. So please get your papers in as soon as you can, okay? That could be today, tomorrow, Thursday, Friday, Monday, or Tuesday. Please get them in sooner rather than later. All right. Any questions? How are we going to wrap up? And again, for those who weren't here when I said it before, if you haven't done the student course evaluations, please do the student course evaluations. Okay? All right. All right. Where we left off last time, any questions either on scheduling or on physical science? Okay. In Chapter 6, we're on page 160. We're electricity and magnetism. We're in the electromagnet section. Okay, this deals with electricity and magnetism. Now, the structure here for electromagnet is a core, okay, a ferromagnetic core. What materials would be in a ferromagnetic core?
Iron, nickel, or cobalt.
Cobalt. And cobalt's pretty rare, so you won't find that. Probably an alloy of iron or iron and nickel, possibly some cobalt in there. Okay? That's your core. And then you have wire wrapped around the core, just like a solenoid is without the core. You have the wire wrapped around the core, and that's what gives it its magnetism. The field is enhanced by the combination of the core and the coil. Okay? The wrapping of the wire. The more turns of the wire, the stronger the field is. The more current, the stronger the field is. Okay? And of course, having the ferromagnetic core makes it stronger as well. The big deal about electromagnets, they can be turned on and off with a switch. When the current is flowing, they're magnetized. When you turn the current off, they're no longer magnetized. Or at least the magnetism goes down big time. Okay? Many, many applications. We'll talk about several of these. Meters, switches, speakers, motors, all these kinds of things use electromagnets. Okay? Seems like we did part of this slide last time, did we? Y'all remember? Nah. Okay. All right. Let's look at our electric meters then. Now, in the last lab and the previous lab, both of the last two labs, we were using the voltmeter. In the last lab, we actually used an ohm meter as well. Both of those meters are built something like this. Okay? Now, of course, those were digital. This is an analog lab. Okay? But you have a strong permanent magnetic field. This is a horseshoe magnet here. Where does the field lines go? In the magnetic field lines. Where do field lines go? So again? North to south. They initiate at north and go toward south. So the field lines would be in this direction. Okay? Pointing from the north to the south. Okay? Strong magnetic field there. Now, when you turn on a current through here, then you've created an electromagnet. And it's, depending on and this will be a DC circuit, by the way. You turn on that, and by the way, back up. Electromagnets, always DC. AC circuits, you can't do an electromagnet. at all because the current's going alternating very, very quickly. Won't make a magnet. You have to have DC current. So you have a DC current, and let's just say the north is pointing this way, upwards. Okay? You turn on the current. Now the north is repelled by this north and attracted to the south, depending on how much current it is. That's how strong the field is, and that's what turns it this way. Now there is a spring here that it's having to work against, so it doesn't just flop over there. It's having to work against the spring. It's calibrated to give you what the voltage is that produces enough current for that to swing there, and that's what your calibration is. Ammeter does the same thing. The more current going through there, the stronger the field, and the more it turns that way. Now an ohm meter, you actually, either they wire it differently or you scale it coming this way, because the greater the resistance, the less current you have going through and the weaker the electric field. So see, all three of those, ohm meters, ammeters, and voltmeters, basically work on the same principle. Okay? So this one happens to be an ammeter, instrument for measuring the current. However, if the current is made constant, then you could be measuring voltage as well, because that varies the current. Uses the magnetic field produced by the current around the coil here. The magnetic field, and hence the deflection are proportional to the current, so you just scale this to read whatever the current flowing through there. If modified, it can become a voltmeter, potential, or going the other way, an ohm meter, which measures resistance. Any questions? Okay. Now, not just meters, switches, electromagnetic switches. Right now, in that little box there, okay, there is a thermometer in there, and it's measuring the temperature. When the temperature reaches a certain level, it's going to shut off the heat to the system. Okay, that's the switch. And relays do sort of the same type thing. Talk first about relays. Uses a low voltage control. Here is the small battery in that. Okay, a very low voltage control. Low voltage use. Relays use low voltage to control currents to switch on larger high voltage currents on and off. Okay, that's a really poorly worded sentence. Relays use low voltage control currents to switch larger high voltage currents on and off. I read it correctly. So it uses this small current here, just introduces a little bit. This is electromagnet, okay? As the electromagnet, you put a current through, then that pulls the switch here against the spring, pulling it, closing the contact, creating, say, your heat pump to come on, your AC system, your ventilation system to come on. So a very small current here controls a big system over here. Now what controls that? Well, here you have mercury in a glass vial, and say when it's, and there's your bimetallic coil, and as that heats up and unwinds or cools off and winds, or whichever way it's going, then it could be the thing that closes the switch here, creating the current here, which pulls this switch, which turns on the system. So that's basically how a switch or a relay works. Now that's showing electromagnet. You can also have solenoid switches. The movable spring-loaded iron core responds to a solenoid field rather than an electromagnetic field. Still the same type principle. You use these for water valves, auto starters, your VCR switches, anything that there you can use a remote. That's what you're doing. When you press a remote, you have a very small battery there, very small current. It does something which then turns on a bigger system. Okay? A lot of automobiles now have remotes that you unlock doors. You can start the car without a switch. Does Toyota? Yeah, Toyota has those. GM. The push. Yeah. many ways we use these. Okay, activations, bells and buzzers. You know, anytime something is coming on, like the fire alarms. Okay, you break that glass, close the current. A small voltage in there alerts the entire alarm system here, and it goes off. So, lots of ways that we use electromagnetic switches and relays. Any questions on that? All right. Other things. Telephones, loudspeakers, microphones, anything like that. You now have a coupling the acoustic waves to the electric currents. Okay? So let's talk about the telephone first. Now these are the old phones. I'm not exactly sure how they do it in a cell phone. It's probably a little bit different from this, but in the old conventional phone here, but the principle's still the same. It's just how it's activated. When you speak into the phone, if you hold your hand in front of your mouth while you're talking, you can feel little pulses of air. That's what sound is, little pulses of air. My vocal cords are making little pulses. They're making the way to your ears, and your ears are receiving those. That's how you can hear me, those who can hear me, okay? These are called the condensations here, the rarefactions in between. These are the pulses. They go through the receiver, the transmitter here, and behind here is a metal diaphragm. You know, behind this, and those pulses push on that diaphragm ever so slightly, and they push the diaphragm, and that pushes carbon granules closer together. The closer together they are, the better conductor it is. Okay? You have a little circuit there, a little power supply there, very, very low voltage. When you close that up, make a better circuit, then you send a signal down the wire. When the rarefaction comes, it comes away, the circuit is turned off. So basically these pulses, the sound pulses, become electrical pulses. Okay? The electrical pulses make their way to the other end, and then on the receiving end, they do the reverse of this. Okay? And we'll see that in speakers. We'll show that in just a second. Okay? But what you're doing as you vibrate the carbon granules, changing the resistance, less resistance when they're compressed together, more resistance when they're further apart. And that all comes because of that vibration from the sound. Okay? Changes the resistance, varies the current. That varying current makes its way to the receiver, and here is the speaker. And for some reason they have extra space here. The electromagnet, shown here, and you have a permanent magnet here and electromagnet here. Okay? You have a paper cone here, and when this electromagnet receives that varying signal that you've got here, the changing current here, it is pulling, repelling or attracting to the permanent magnet, pulling back this paper cone, which then creates sound waves. As it pulses coming out, the electrical pulses coming in, vary that comes out, and you hear it. Now, it's remarkable to me how not only does it transmit sound, but it even transmits things like tones and stuff. Most people, I'm guessing, if it's someone you know their voice, you pick it up. Not only can you tell someone's talking, you can actually pick up enough about the harmonics and the tones and things of their voice, you can usually tell who it is. Okay? Not always. I'm hard of hearing, and my father-in-law has a frequency that I'm really, really bad on. Just about every time if he's calling, usually calling for my wife, his daughter, I say, well, this is, and I thought, oh, it's probably Mr. Brazil, okay? I just don't pick up his, because I have certain frequencies I have a really bad hearing also. So he speaks in those frequencies, which is not good, okay? For me anyway. Okay. So this is how it happens. The compressions in your vibrations in the air waves, that's creates the electrical signal here, the electrical signal, and the electromagnet here creates a vibrational wave that comes out of the paper cone. And there you have your sign. Amazing how they do it so well. Now, cell phones do a lot of this electronically as opposed to analog. You know, you're not actually making, but I mean, ultimately it has to make the waves. How it does that, I'm not absolutely sure, but it's a lot more electronics probably than, and it's probably digital, you know, rather than analog like this is. Okay. Another use, before I turn the page here, there is a concept supplied here called a lemon battery. And did I tell you about Galvani and his frog leg? Yeah, okay. Same type principle here. Two different pieces of metal. One a copper wire, one a paper clip, which is mostly steel, okay, into a lemon, okay? And then wrap that around something, you created a circuit, okay? You've just made a little lemon battery is what they call that. Second? I don't know. It depends on, let's see if they indicate. It's all depends on what they call the electronegativity difference between the iron and the copper. So that's really all that matters. The lemon juice provides the electrolyte, and it's as good as any. And so it just depends on that. Now, how close you put the wires and how far apart, that would also influence it a little bit. But it's basically the difference, the potential difference between copper and iron. Use different metals and you can actually create different potential differences. Okay, the one they show here is copper and iron. Okay, you can use materials shown here or any other. Now, this is one class where I hesitate to ask this question because I think I know the answer anyway. Have you ever had a battery in your mouth?
No. Yes. No.
Okay. Yes.
Again, what same person would have a battery?
Okay. Okay. That's why I hesitate to ask in a room full of guys, especially automotive type guys. Okay. But even if you haven't put a battery in your mouth, I bet you've had one in there. Have you ever bit down on a piece of aluminum foil?
Yes.
Did you notice anything? Okay, I bet you then you have a filling in the tooth, right? The filling in the tooth is a silver composite, okay? That's one metal. Aluminum is a different metal. You bite down on it, and your saliva makes a great electrolyte. Yeah, I couldn't think of the word. It makes a great electrolyte, and that's why you feel the jolt, okay? If you've ever bit on a piece of aluminum and felt that, you've had a battery in your mouth. You didn't put it there intentionally, but you had one. You have created a potential difference between the silver and the aluminum in the presence of a good electrolyte, saliva. And boy, you sent a jolt, because right below your filling is your nerve, okay? Because the nerve is not too far into the tooth. You don't feel much in the tooth, but there is a nerve there. And you send that jolt through there, and you know it, okay? So whether you realize it or not, you may have had a battery in your mouth, if you've had a feeling. Now, if you have perfect teeth and never had a feeling, you're not going to notice it if you bite down on a piece of aluminum. It won't matter to you at all. But if you have a silver composite filling, I actually have one gold filling that probably would do the same type thing. I don't go around testing it, though, because it doesn't feel that good, okay? All right, then on page 161, electric motors. Another use of electromagnets, okay? These convert electrical energy into mechanical energy, okay? How do they do that? They have just two working parts, okay? First, they have the strong field magnet. You always have this in every one of these devices, your meters and everything else. you have something that creates a electric field, a magnetic field. Which way do the field lines go?
North to south.
From north to south. This time they put the north over here, south over here. So the field lines are going this way. Okay? Now, that field magnet is stationary. Okay? Then you have the armature that's movable, and that's the electromagnet. All right? Now, what you do here, you're taking electrical energy, converting it to magnetic energy. Here's how you do that. The electrical energy comes in here in the form of current. That creates a strong magnetic field here. Okay? Some of this looks like it's a little unnecessary. But anyway, you're also sending that current through here, and the windings have to be just so that when the current is flowing through here, that becomes, let's say it's going, here's the electron current this way, your conventional current would be going the opposite way, and that creates the north magnetic field in this direction. Okay? Once you've created that, that's repelled by this one. Of course, that makes the south magnetic pole here. It's repelled by this one, so it starts at turning. Now, they're showing brushes here. Why brushes? Anyone know? Well, if this is all you had, then it would turn this way until north was lined up with south, south was lined up with north. It would stop right there. Wouldn't be a very good motor, right? It would turn about half a turn and stop. But what the brushes do, they reverse polarity. Because this is, well, or another thing you could have is AC, and if it's AC, it's reversing its own polarity, and it really gets it spinning then, okay? So either one of those will do it, but if you have brushes here and you have what they call a commutator ring there, or something that's equivalent to that, once it turns halfway around, it reverses the polarity, so this becomes the south, that becomes the north, and then it's repelled again another half turn, and that keeps the motor running. Converting electrical energy here into mechanical energy, the energy of motion. Your weed eaters, electric lawnmower if you have one, anything such as that, that when you turn it on, you get motion, start a current, that's what you've got going on there. Okay? The armature rotates by interactions with the field magnet. Okay, this is the field magnet. The commutator, here's the commutator, and the brushes reverse current every half turn. So it turns half a turn getting the north over here to the south. Right about the time it gets there, then the brushes switch your polarity, so that this suddenly becomes the south, that becomes the north, and then it repels again, and it repels every half turn, and goes pretty smoothly from there on. Okay? Now, they also have, the reason they showed more sort of a bulbous thing here, you want to have more mass there, so it sort of acts like a flywheel that smooths it out, so you don't have any jerking going on there. That inertia keeps it moving pretty smoothly. That's basically what a flywheel does for you, right? Yes.
How do a taser work?
Okay.
How do they get it charged? Do they have to charge it up overnight or something?
Yeah, for sure. It has a capacitor, I'm guessing. Anyone know anything about tasers? My guess is a capacitor which stores a charge, and then when you activate it, it releases a pretty large amount of current in a burst. And I'm guessing that's how it works. I've never handled one. Don't want to handle one, you know. But that's my guess of how it does. It probably has a capacitor in it, a pretty heavy capacitor, which will then release a sudden jolt of juice. I'm just guessing at it, but that's my guess. Now, we aren't talking about capacitors. That's a little more advanced than what we're going to do in here. Y'all probably deal with capacitors. Not that much.
Not really.
Okay.
They're not ECUs, but we don't ever rebuild our ECUs.
Well, actually, have any of you ever turned the knob on the radio? You're dealing with capacitors. You're changing the capacitance. That capacitance changes the frequency that you're listening to. That's how it works, okay? So, yeah, you have dealt with them whether you realize it or not. These lights have a pretty strong capacitor in there that gives you enough voltage to send those electrons flying back and forth and give you the juice there. All right, now let's move the other way. Electric motor takes electrical energy and converts it to mechanical energy. Electromagnetic induction, and by the way, this is on page, this is starting section 6.5 on page 162. This is going to enable us to generate electricity. In other words, to take mechanical energy and convert it into electrical energy. Now, this is the first stage of it. Okay? The reason electromagnetic induction works, okay, I want to remind you, what produces a magnetic field? Does anyone remember? Always what produces a magnetic field?
The flow of electrons.
Say again?
The flow of electrons?
Yes, the movement of charge. It doesn't have to be electrons, but the movement of charge. Usually it is electrons. Movement of charge creates a magnetic field. Similarly, the relative motion between a magnetic field and a conductor is going to create electrical charge, a field. Changing magnetic fields near a conductor is going to induce a voltage. And we're going to do this in the lab. Hopefully we're going to have time to get it done today. The effect is you get an induced voltage and therefore an induced current. All right? Now this shows us having just a coil of wire here, an ammeter here, okay, and a bar magnet. Guess what? No power supply at all. None. Nada. Zero. None. And you drop the bar magnet here. Well, what the bar magnet, what's around the North Pole? Concentration of field lines. What's around the South Pole? Concentration of field lines. Now, these are going in opposite directions, but when that North Pole goes through the coil of wire, you have a changing magnetic field through a coil of wire, you create a current. That's electromagnetic induction. Okay? Now, if you were to drop this, you see, this is just showing the current goes slightly positive. Okay? If you let it fall on and the south falls through, you'll see it goes negative. Or, if you push it up through here and the south goes through, that creates negative. If you continue pushing up or pulling up, then when the north goes through, it goes positive. So, depending on the number of field lines being crossed, okay, by the coil, and the speed at which you do, the number of coils in the turns in the coil, all that will determine how much current you create. The induced voltage depends on the number of loops, number of turns, the strength of the magnetic field. If this is a very weak magnet, it's just going to put a little bit. Very strong magnet, it's going to be a lot more current. And the rate at which the magnetic field changes. So if you just lower it real gently through there, you'll see it. If you go rapidly, you'll see it much more distinct. Okay? And then, of course, the direction. What kind of field is going through that will change the polarity of the current as well. Okay? Make sense? That's electromagnetic induction. Real quick and dirty here. That leads to, there's a little blurb here on a simple generator, and you can certainly read through that, and I think you'll find pretty simple, something you probably could put together yourself if you wanted to. Now, before I move too much further here, at the top of page 163, there is a really interesting little blurb here. And if some of you haven't chosen a paper topic, if this is something of interest to you, you probably recognize at least one of these names and probably both. Okay? In fact, there's several names in here that you might recognize. If I talked about electrical inventors, who comes to mind?
Tesla, Edison.
All right, you just nailed it.
Franklin.
Oh, Franklin also. Edison and Tesla came much later than Franklin.
Yeah.
Okay? Thomas Edison probably, he pretty close to holds the record for the number of patents under one person's name. I mean, if anyone else is close, that's surprising to me. There could be somebody patented a lot of little dinky little stuff, but Edison patented tons of really, really useful stuff. Light bulbs, phonographs, I mean, you name it almost, and he did it. Brilliant mind. Actually, he was in an accident when he was young and lost a lot of his hearing. And he attributed that to the fact that then he could focus on what he was thinking of and sort of tune out everything else. And that may have been part of his genius, is that he was able to tune everything else out. But anyway, he was a brilliant electrical person. However, back at the time, there was a big debate going on. Okay? Direct current was considered safer. Alternating current was considered pretty dangerous. Yes?
Was it Tesla who came up with the alternating current?
Tesla was the champion of the alternating current, and Edison was the champion of DC. Edison lost on that one. Okay? Actually, Tesla worked in Edison's lab. He was an employee of Edison. They were pretty good together. I don't think they got along together well, but the two great minds, they really worked well. But Tesla was convinced they needed to go in the direction of alternating current, and Edison was so stubborn he refused to, so they did split off. Second?
Just read my paper, you'll learn all about them.
Yeah, okay, exactly. Very good. There's another guy whose name is in here that you could also write about. George Westinghouse. There's a whole set of appliances called Westinghouse appliances named after him. He hired Tesla away from Edison because he was convinced by Tesla, I think, that AC was the way to go. And he, I think, made a good bit of money. Poor old Nikola Tesla never made a lot of money. He would reinvest it in more of his projects, and he just wound up not ever making much money. But he invented so many incredible things. Edison did okay with money-wise too, but Westinghouse, I think, was the businessman, and he came out ahead. Now, my uncle, who was I want to say civil engineer, I think he was, but he did a lot of mix of engineering. He didn't like Westinghouse products very much, so he called it "We Sting Who Use." Okay, he put an extra W in there, but Westinghouse products are pretty good. Okay. Tesla, by the way, was born in Croatia, and way back, many years ago, I'm guessing more than a decade ago, in my automotive class, just like this one, I had a guy in there who was a Croat. You know, he had moved here from Croatia shortly after the Balkan Wars. He and his family came over. And later, I think his brother or cousin or somebody else was, I can't remember their names now. He was so proud of Tesla, he wrote his paper on Tesla because he was probably the most famous Croat that I know about anyway. And of course, what is Tesla known for now? Who uses that name? Second? The cars, yes. It's a strictly electrical car company. They don't do any internal combustion at all, do they?
No.
Yeah, strictly electrical. And I don't remember the guy's name who does that, but anyway. Huh?
Elon Musk.
Okay, and he...
Same guy who does the SpaceX program.
SpaceX program, yeah. Pretty incredible mind there, too. Has he made a lot of money? Yeah, okay. A lot of times people like that are like Tesla, and they come up with all these great ideas, but they spend all their money developing them. But he's made tons of it, too. Huh? Okay. So he must be a good businessman, too. Okay.
Or a good liar.
Okay. Or he could be a politician. Well, that's you said that. Okay, never mind. Okay. All right. But anyway, I wanted to hit that before we moved on. So let's move now to generators. And that's exactly what electrical induction does for you, is enable you to generate electricity using mechanical energy to produce electrical energy. And frankly, folks, an electric motor and electric generator are almost the same devices that just wired backwards from each other. That's really the truth. So one takes mechanical and makes it into electrical, the other takes electrical, moves it to makes it mechanical. So the structure here is so similar. You have an axle with main wire loops in a magnetic field, just like we saw with a electric motor, okay? It almost looks the same. Here's your magnetic field. Okay, they turned it upside down. That's okay. And frankly, this doesn't have to be a permanent magnet. It looks like it is, but you can wire it so this is like a magnet itself. I think the other one was too, but it was just such a confusing drawing. Which way do the field lines go?
North to south.
From north to south. You see, they drew the field lines in here. Okay? So what you have here is a strong magnetic field, whether a permanent magnet or an electromagnet. This shows that it's probably an electromagnet in this case. Strong field here, and what you have is something, mechanical energy is making this turn. Okay? Now, if any of you, I'm sure you have before, started a lawnmower or something, you pull on it, you get it going, and then it sort of keeps itself going. Well, that's right. You create the turning here, and when this turns, see, right now it's cutting the most number of field lines it can cut. If you turn this, the number of field lines decreases, right, that are being cut by that coil, okay? Decreases until when you're here, there's 0 field lines being cut. But then they start increasing when it turns a little further until it gets maximum again, but now the current is going in the other direction. Now, take me back to what creates a magnetic field?
The movement of
Moving a charge, exactly. What creates an electric field? Changing magnetic field.
Okay.
So you're changing the magnetic field being cut by this coil when you're turning. And when you do turn it, that then creates electrical field. And this would normally be, and it is, the way they designed it here, alternating current. Because this way it would be decreasing, then it would be increasing, but in the opposite direction, max again, decreasing so it goes the other, so your current is going like this. Sometimes positive, sometimes negative, sometimes positive, sometimes negative, because of the field lines being cut by that coil. Now, it's not just a single coil. It's a whole bunch of coils there. The more coils you have, the stronger the AC, and this is the AC generator here, by the way. These are connections for the alternating current. One of these goes one way, one goes the other, okay? Now, you have to turn this to create the electrical, to generate the electrical energy, and it is generated as alternating current here because of the twisting there. So this is an AC generator. The axle is turned mechanically to produce electrical energy. What turns it?
A belt.
It could be. But if you're generating electricity, what are some generating sources?
Wind.
Wind, certainly. If you had a windmill, one of those wind turbines there, that could be creating the mechanical energy here, twisting this in the presence of the magnetic field, so you're changing the field, going through the loop, creating an electrical field that creates an alternating current. It could be wind. What else could it be?
Water.
Water going over the dam, your hydroelectric dam. That could be what's doing it. What else? Sending high energy steam through a steam turbine. How could you get that high energy steam? Nuclear, oil, natural gas, anything that is going to give you the energy to create the steam. So you see, all that stuff we studied in energy here is being put to the practice here. The renewables are wind and water. The fossil fuels would be your natural gas, your oil, your coal, whatever is turning, creating the heat there that sends the steam through the turbine, or the nuclear would be creating lots of heat, and that sends the steam through the turbine. So this would be your alternating current. The sign of the current and the voltage alternate. Current and voltage alternate. Halfway around it's positive, then it goes to zero. The other half is negative, coming back to zero, positive again, positive, negative, positive, negative. Can you have a DC generator?
Apparently.
Yes, you can, and here's how they do that to make direct current. It's not uniform direct current, but here's what you do then. What you have now, notice here, here's your rings here. Before it was a solid ring, two solid rings. One brush was on one ring, one on the other. Now both brushes are on different halves of the ring because here you have a split ring. Okay? And this is called a split ring commutator. Okay? Because halfway around here, you've got the current flowing in one direction. The positive, just like it was before, but right when it was going to go negative, it flips the sides. It goes across the gap here, and the one that was coming in positive now comes in negative. But you flip it, so you get the pulse DC. It's always positive, not evenly positive. You get electronics in there to smooth that out, and that gives you your DC, direct current generator. The sign of the current and the voltage is constant because every half time around, when it would go negative, then it flips the different ring, and if this was positive halfway around to here, then right the time it went negative, it goes over here. Well, this is the negative side here, so it becomes negative. This one becomes positive. So it keeps going a positive current, DC generator. Split ring commutator. What do y'all use in cars now? It used to use a split ring commutator. What do they use now as your alternator? Isn't it sort of a dual or tri-diode system? Okay. I don't think you have the commutators anymore. In the old days, they did.
It's a triangle.
Yeah, I think it's a
Triangle.
yeah, and it's a, what did I just say? Diodes. 3 diodes set up a certain way that always keeps it.
No, I just never read that.
Diode bridge inside.
Is that what it's called?
Inside we call it diode bridge.
Right. Because your generator is actually producing AC. But once it goes halfway around, then it hits the other diode. The diode only sends current in one direction, won't send it both. So you have one going one way, then one going the other. So you always keep the current going in the same direction. Because you've got to have that. Otherwise, you would be charging the battery half a cycle and discharging half a cycle. You'd never charge it. So you have to have something in there, a split ring commutator or a dual or tri-diode to say diode bridge, is that what it's called? To keep it DC, to change it to a DC current. Make sense? All right. All right. After generators, we have transformers. Now, these are not things that go flying around. That's cartoons, you know. These transformers. Okay, glad you're listening. Okay, all right, all right. Here's the issue. Remember back the current wars. Edison liked DC, but man, what's the biggest battery you've ever seen? How many volts?
18-volt tractor battery.
Oh, you have seen one. On some tractors and heavy equipment, I've seen as high as 24 or 36, I believe. Big old long batteries, okay. Really heavy-duty equipment. That's about all you can get. What can you get voltage in a AC? Way more than 18, way more than 24, way more than 36. What's this? 120, okay? So, way better off, but there is where Edison was afraid alternating current with high voltage could kill you so easily. Or any current can kill you, okay? And it's not really the voltage that kills you, it's the current, okay? We'll talk about that a little bit later. Maybe we already have, I can't remember. But anyway, when you're sending, okay, where's the closest generating plant? Anyone know? Or a generating plant?
Like, I drive past one on my way to work every day. There's Gorgas Steam Plant.
Gorgas Steam Plant. So
And
you're
then
coming
there's
from up
the
that
other
way.
one on the side of 22.
Okay.
I can't remember the name of it.
Yeah, you're coming from Jasper or somewhere? Yeah, okay. Yeah, we go to the lake that way, so yeah. Yeah, big old steam plants there. Well, they got to get the energy from there, which is out in the middle of nowhere, right?
Field lines.
Huh?
Field lines.
Yeah, field lines. Okay, now if you're sending current through a line, the best lines you can get always have some resistance. And remember what the factors for resistance were? One was length. The longer the line, the more resistance. So long way from the generating plant, you're going to lose a lot. So how do they deal with that?
Substation.
Say again?
Substation.
And what do they do for you?
I don't know the answer to that, but I know what.
That's what they do. You're absolutely right. What they do, you see, resistance depends on your current, right?
Yes.
So if you can drop the current, you don't have as much resistance. But if you drop the current, you have to increase the voltage. That's what transformers do. You have step-up transformers and step-down transformers. At the power plant, they're stepping up the voltage as high as they can go, and I mean ultra-high voltage, okay? Sending it very little current, so they have very little line loss. But then when they get into a community, that's where your substations are, and they'll have one and then another and another, and the final one is just outside your home, okay? Because that's going to create a fair amount of current when you drop the voltage that time. You don't want to have a lot of line loss, so that's usually within
About
40 feet, 50 feet of your house. That last leg, and you don't have that far to go. So that's what your transformers are doing. These transformers are doing for you. The ones that squirrels like to, okay. When you have high current, you have high resistive losses. If you have high voltages, that's dangerous potential differences, okay? So you don't want high voltages in your home, but you don't want to have amperage, high currents, on the field lines, okay? So what you have are transformers to raise the voltage or drop the voltage depending on where you have. So the solution are these transformers that either boost the voltage and or current or lower the voltage or current, the AC currents and voltages. And guess what? These transformers only work with AC. They do not work with DC. Because what is it that creates an electric field? Changing current. And what creates a magnetic field? Changing charge. Yeah, okay, so you've got these things going on. You have to have AC, that change going on, for you to be able to use these transformers. So here's the basic relationships. It's really your conservation of energy. They say power in, power out. Really better say energy in and energy out. But whichever. Actually, power is good here too, because we are measuring in watts. Your watts in is always going to equal to watts out. However, remember what power was in an electrical sense? It kind of looks like Ohm's law, but it's different. What's your power formula? Current times voltage. Excellent. Okay. Let me change my pen. Okay. So power is equal to current times voltage. So therefore, if you have a low current, high voltage, that gives you a certain power. A transformer can change it to a high current, low voltage, but you still got the same power. The power in is power out. That's what the basic thing is. Now, how do we do that? The number of coils. Okay? Now, they don't show a very good picture here. Let's see if there's one in your book. Yeah, we'll get to it. We'll get to it in just a few minutes. Here is the deal here. The voltage on the primary side, that's the input side, is related to the number of coils on the input side. I wish we had the figure here. And that ratio is the same as the voltage on the secondary side, the output side, to the number of coils on the output side. This number of turns here, the voltage here. And this ratio is the same. The ratio is the same. The numbers are different, but the ratios are the same. Okay, they have to be. Let's see if we can get a better picture. This is not the way to start it, but okay, let me get this off of here. Whoops, not that, this. Okay. Here's the primary side. Let's say we have 120 volts on this end of the transformer. Let's say you have 10 turns. Okay, this is a ferromagnetic coil. Okay, it just happens to be a loop here. 120 volts coming in, 10 turns. Okay, this is going to create, and this is alternating current. This is going to create a varying magnetic field in your your ferromagnetic material here. Okay, varying electric field here. Over here, but you only have one turn on the outside. So you're going to drop your voltage from 120, well, 120 over 10, that's 12, and you're going to have on the secondary side 12 over 1. You're going to have 12 volts here, because only one turn there. Have any of you ever done any outdoor lighting? Outdoor lighting, as in, when you're trying to show off the house and that kind of stuff. You want that usually to be low voltage. We put in a system in our house, and I think we had 6 volts. So it was 120 coming in, 6 volts going out. Okay? And what we had were transformers. And the big old boxes there, that's what it was doing. So you didn't have such high voltage there, so you wouldn't fry as many squirrels maybe, and that kind of stuff. Okay? If you had 120 going in and only one turn here, 120 to 1, that ratio is now be 120 to 1. Over here, if you had 10 turns here, you have 1,200 volts going out. Your secondary is going to be the same 120 to 1 ratio, but if you have 10 turns here, that makes 1,200 volts out. You've really stepped up. This is a step-down transformer. That's a step-up transformer. You take whatever voltage you have, and if you decrease the voltage, that's step down. You've increased current, by the way, but if you have it the other way, where you have step down up the voltage, you've actually dropped the current. The one coming into your house, which is that? Step up or step down? Step down. Step down, because it's probably at least 360 out there, maybe even way more than that. You're trying to get it to either 240 or 120 coming into your house. I think they actually bring it in as either 360 or 240, and then they split it off. And that going to your clothes dryer, your oven, and the high energy things, high current type things, those are going in as 240, and the others are 120. So that's how this works. So here's your simple formula. This is one that you'll need on the test, is how these things work. And then also the one we had up there, that power is equal to voltage times current. Because if you change the voltage, if you step down the voltage, you're stepping up the current. If you're stepping up the voltage, you're stepping down the current, because of that power relationship. Does that make sense? Okay. Let's do example 6.9. Okay. Let's see if I can find some clean board to work on. Ah, here's some. 6.9, example 6.9 on page 164. A step-up transformer has 5 loops in the primary coil. 5 loops, lops, okay. Five loops in the primary coil. What symbol do we have for that? What was that called?
VP.
No, that's voltage. Okay. Whoops, went the wrong way. That's your N, number of loops. Okay? All right. So this is N sub what? P, primary. There's your N sub P. And 20 loops on the secondary coil. 20 loops secondary. So what would that be? That's N sub S. Very good. Okay? If the primary coil is supplied with an alternating current at 120 volts, what would that be? What would that be? That's your V sub P. Okay? The question is, what would be the voltage in the secondary coil? This is the unknown, and you're looking for V sub S. Okay? And what was the equation that worked for that?
It was
Second?
V sub P.
V sub P over N sub P,
Equals V sub S.
V sub S over N sub S. And what was our V sub P?
120.
120 volts over
Over 5.
5 loops would be V sub S, that's the unknown, that's what we're looking for, over 20. Okay? Now, how could you solve that ratio? Proportion. 2 ratios equal to each other is a proportion. How do you solve it? Anyone know? Simple little technique called cross multiplying. Okay? That would be 5Vs is equal to 120 times 20. Okay? So this will be 5, well, let's go on and divide by 5. Vs, divide both sides by 5. 5 will go into 20 4 times. 4 times 120 is 480 volts. 480 volts. So what kind of transformer was that? Step up transformer, because you went from a low voltage to a higher voltage. The other way you could look at that is rearrange these, you know, and you see you got a 4-to-1 ratio here, so it's going to be a 4-to-1 ratio here. You multiplied that by 4. All right. 480 volts. Very good. Now, a step up or step down transformer steps up or down the voltage, but then it does exactly the opposite to the current. Okay? So your formula there, if you go back to that first thing that we had here, power in equal power out, what would that be? Power in equal power out. And you could call that power on the primary side is equal to power on the secondary side. To me, that makes more sense. But in and out works well too. Just remember, primary is on the inside and secondary is on the outside. And what did y'all tell me that power was? Current, so that'd be IP VP is equal to IS VS, right? Now, the problem we just had, let's see if that's the same one. Yeah, the step-up transformer in, so let's go back to, well, we'll do it here. What was our power in, VP? I mean the voltage in? Okay, let me read the problem first. Step-up transformer in example 6.9 that we just talked about is supplied with an alternating current at 120 volts and a current of 10 amps in the primary coil. So what would that be? 10 amps? What in that picture is 10 amps on the primary side? Amps measures. Second? I can't hear. 10.0, but what symbol does that represent here? I, okay? So this would be 10.0 amps times what was the primary voltage? 120 volts. That's equal to, and we want to know what was the current on the secondary side. So this is the unknown here, I sub S, and what was the voltage on the secondary side? We just did it. Previous problem. 480. And that was your volts. Okay? So what you can do here is divide both sides by 480. Right? So that goes out there. The volts go out here. 120 will go in the 480 exactly 4 times. So it would be 10 divided by 4, which is 2.5. 2.5 what? Amps. So with a step-up transformer, you're stepping up the voltage, but you're stepping down the current because they go in opposite directions there. So sure enough, you started with 10, you wound up with 2.5. And again, it's that factor of 4. Okay? So there in your text, you'll see 2.5 amps is your final current. All right, good deal. Now, before we get to circuit connections, there is another concept supplied on page 165. And this is really an interesting thing. If you've ever seen one happen, it's really pretty, almost amazing to watch these things. I don't know how many of you have your books, but if you have a support up here and you have a coil of wire, you don't have any power supply in this. No batteries, nothing else, but you have a magnet sitting down here. And then you have another support over here with a coil of wire over another magnet. Okay? No power supply, no source of energy. If what you do is get this one to swinging, guess what this does? It starts swinging in the opposite direction. So you can make this move without touching it, without introducing anything. But why does that happen? Because this coil of wire is cutting magnetic field lines. You're inducing a current in that electromagnetic induction, and that current's going through here. That alternating current then is going to interact with the magnetic field and create motion there too. Pretty incredible. They call them swinging coils. It's almost like magic. I mean, it's actually kinetic energy becoming electrical, and that going back to kinetic. Okay.
Break time.
Is it break time? Okay. We'll pick up then after the break. Try to keep it 5 minutes or less with circuit connections. Okay? I'll put this on pause right now. All right. As soon as the projector will warm up here, here it comes. We're now in 6.6. These are circuit connections, okay? And again, it's talking about some of the stuff we were mentioning before, alternating current versus direct current. Now, as we mentioned before, most of the current that you generate in your automobile engines, in the generating plants, that's almost always alternating current, okay? Now, what you get from a battery, that's DC, okay? But most of the generation capacity is alternating current. Wind turbines, water, whatever. Now, one exception to that, solar. Solar is DC, okay? That is, you generate that with solar cells and the devices that are in the electronics that are in that produces DC, not alternating, okay? But just about all the others generated is alternating current. Now, yes?
If direct current is used in cell phones and iPods and
air conditioning system, the vents, just about everything, your ranges, your ovens, your things, all that is alternating
So
current.
it's not as popular as direct current, but it's more effective, right?
It depends on what you're using it for, yeah. Whenever you're dealing with low currents, that's a real gross generalization, low currents, DC is usually better. And that's why these things are really low current. But light bulbs and anything produces a lot of heat, that's going to be alternating, almost exclusively. But that's not all. I mean, it's just how things are designed. Okay? Now, the alternating current is transmitted over high voltage lines, stepped down for use in homes and industry, stepped up to transmit. And the big advantage of alternating current is that you can step it up and down. When you're transmitted it, you can have high voltages on those huge lines that go way up in the air. No one gets close to them. You know, they're not going to, be bothering anyone. Now, we had some friends who were thinking of moving out to a certain area, and the woman got really concerned because there was a high voltage lines going through there. She was afraid that would damage her kids, somehow. I don't think anything's ever been shown that there is some danger there, but because there was a possibility, she didn't want to move out to that neighborhood. Okay? But anyway, much of what you do to transmit AC, that's the way to go. And that's where Tesla and Westinghouse beat out Edison, because they really hit that one on the nail on the head there. That's the way to go. Direct current, though, automobiles, cell phones, all your little portable electronics, your calculators, your all those things, laptops and stuff. This is DC here. How can you tell? Looky here. Now, sometimes they'll call this a transformer. This really isn't. Is a converter. It's changing AC, and you see the big old wire here. Very different wire coming out, DC. This is a direct current wire. This is alternating current. Okay, and it can be as little as a little. When you plug your cell phone in to the wall, I bet you have a little box there that's between the plug-in and what comes out. And that little bitty wire coming out, that's DC. It's AC up till then. Okay, so movable, portable applications, almost always DC. Anything that runs on a battery. And batteries are in just about everything in your automobile. The main current source is chemical batteries. That's where it comes from. That potential difference between the iron electrode and the copper electrode, between the zinc and the carbon, whatever your thing, lead and lead sulfate. You got a potential difference there. You have a series of those together. That's your current source, and that's DC current. It always flows in one direction. Alternating is back and forth, back and forth, back and forth. So let's look at the voltage sources in circuits. Now, we already did this in some of our labs. I'm sorry the labs don't match up with the chapters too well here, but y'all tend to peg it pretty well, okay? There are different things you can put in series and different things you can put in parallel, and you have to be careful with these. Here we're showing voltage sources in circuits. If a voltage source is in series, what you have here is your volts is negative to positive to negative to positive to negative to positive to negative to positive. What are you doing when you connect them in series like this?
Increasing the voltage.
Increasing the voltage, absolutely. These dry cells are typically about 1.5 volts. So that'd be 1.5 volts, another 1.5, another 1.5. That would be 4.5 volts across this. Because when you connect your voltage source in series, you increase the voltage. Okay? The same current goes through all those. Same current goes through it all. you're just increasing the voltage. Okay? Negative terminal of one cell to a positive terminal of the next cell. The total voltage is the sum of the single cell voltages. You have a single current pathway, so the same current flows through everything there. So, how would that bulb, if it's the same bulb, be different if you only had one cell here? It would be a dimmer bulb. 2 would be a little bit brighter, 3 would be the brightest. Okay? That's what we did in that lab when we changed our voltage on the power supply. Okay? That's if you put the voltage in series. Now, you could also put voltages in parallel. Voltages in parallel, you put the plus to plus to plus and minus to minus to minus. Okay? What are you doing on this one? Yes?
I thought the point of power, even a magnet, was you put positive and negative together. It seems like they're parallel. They're like at the same range, you know, negative, 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 and positive, positive, positive.
Yeah.
How does that generate power if they're not,
Okay.
you know, opposite?
That's a very good question. Okay? What is happening here? Say, if this was a 1.5 volt, that's 1.5 volt, 1.5 volt. What's your voltage across this bulb?
The voltage stays the same.
The voltage stays the same because you only have a 1.5 volt across either one of them. What changes here, though?
Amperage.
Okay, your amperage, but not really. If your resistor is the same and the voltage is the same, then the amperage doesn't. What changes is the charge. Charge, because you have 3 times as many plates. So you have more sources for the charge. So what this does for you is extend the lifetime.
Oh,
Okay? So if you had this out there in a remote station and you were recording something, monitoring something, and it was a really hard climb to get there, you want to put your batteries in parallel so you don't have to go out there and change batteries as frequently. Right? So this extends the life. All the negative terminals, so that's what it's doing for you. Not increasing voltage, it's increasing your charge. So it lasts longer. Okay? All negative terminals are connected, positive terminals are connected. The resultant voltage is determined by the largest cell voltage. Now, if this was a 2, a 1.5, and 1.5, that would be a 2, okay? Because the largest voltage difference is what carries over, okay? This makes greater electrical energy available, which means for a longer time. This increases the charge that you're able to do. So it extends the lifetime of your batteries because they don't have to supply as much. Okay? That bulb would be just as dull as one this across here, because that would be a 1.5 or whatever that would be. That would be what you would have. Except that would run down this battery much faster. Okay? Now, but this way, you're providing higher voltage, so you get more current, brighter light, that's going to run down really fast. Okay? Because, and also burn out the bulb faster. Okay? Because you're sending more juice through it. Okay, so that's your voltage sources, both in series and in parallel. Okay? This time we're going to put the resistances in. This one would be which? Your resistors here are in series. Okay? Because the same current goes through every resistor. Okay? Now, I usually point my finger in the direction of the conventional current. They just love the electron current, which flows the opposite direction, but we did that in lab too. So this is your resistors in series. Now what happens here, the total resistance is the sum of all your components. Just like the batteries in series, you add the voltages. With your resistors in series, you add the resistances. Okay? Now, what happens then? This, say, is a 1.5 volt battery. Let's just say that's a dry cell 1.5 volts. Okay, if all these three are the same, guess what the voltage drop across this is? 0.5. And another 0.5 and another 0.5, that adds up to 1.5. Right? So you see your voltage across each lamp is 1/3 if these are equal resistors of what it would be across the battery there, because you're splitting the voltage among each of those resistors. Okay? Would these lights be bright, dim, or what? Dim, absolutely, because you've just got so much current and you got less voltage across one, so it can't have as much brightness to it. Okay? The current drops, the more elements you have. Yes?
I'm sorry, they're all sharing. I was going to say they're all sharing the
Same current,
so
exactly. Exactly. Okay. So the total resistance is the sum of all the components. So if your resistance is greater, same voltage, greater resistance, that gives you less current, so less brightness. Very good. Y'all are good at this. Okay? So here is what you would have. Your resistors add the resistance. Whatever those three resistors were, if they were the same, that would be 3 times R. If they were different resistors, then you just add up the R's. And the total resistance gets bigger and bigger the more resistors you put in there. That's a series connection when your resistors are in series. Okay? That drops the current because you get more and more resistance there for the same voltage in the circuit. So every one you add, less current goes through. Now, your parallel connections. Okay? This one, and y'all were very good on the lab on this one, more than one current path is available. Now, let's go back to this one. Okay? What happens if you take this bulb out?
All circuit dies.
Yeah, all dies because you're only one circuit here. There's only one pathway that the current can get around there. Only one. You break the circuit anywhere, everything goes out. Okay?
Like Christmas lights.
The old Christmas lights. Okay. Nowadays they have them in a sort of a parallel type thing. But in the old days, that was such a pain in the neck. Okay, I can remember my dad really messing with those, not liking them much. So here's what we have. With a parallel connection, you have more than one current path available. We'll see that when it comes up. The overall resistance, believe it or not, drops the more resistors you put in there. It seems counterintuitive, but it really does. The total circuit current increases as you add more elements. So here's your parallel. Now notice here, let's just say a charge goes up here. Some current goes this way, some keeps like that, some goes that way, and some goes this way. So guess what? What's the voltage across this one? 1.5. Voltage across this one? 1.5. Voltage across this one? 1.5. You have the same voltage across these. In series, it was 0.5, 0.5, 0.5. Parallel, same voltage across. Okay? So what's happening here, though? Your current gets split, not the voltage, but the current. In a series circuit, the same current goes through every element. Now some current goes through here, some goes through there, and some goes through there. You have multiple paths. That's why they say more than one current path is available. You take out one of these bulbs, what happens?
It drops. It stops working.
This one stops, and these two keep going because you still have a connection here. You have a complete path around. So skip that, or skip that, or skip that. But the other two stay lit, right? Okay.
Is it because they have different wires while the other one, it's like a shared wire?
Yeah, kind of like that. And if you look at the new Christmas lights, you'll see there's always loops going between each light, so that provides this parallel type setup. Okay. The old days it was one wire, one wire, one wire. One of them goes out, you have to go test every bulb in the circuit. It was a pain, a real big pain. All right, now, which battery is going to run down faster? That one or that one? No, actually, this one, because you have the same voltage going through 3 times the resistance, you have less current, so the battery lasts longer. This one, however, this has to provide the same current to this one and that one and that one, so it's taking more current off the battery, and that's what runs down the battery. In fact, how do you measure battery strength?
Average amps and volts.
Not quite.
No.
Amp hours.
Oh.
Notice that on the thing. It's sort of like power, energy. That's exactly what you're doing. Is how much charge that a battery can produce, and that would be amp hours, because current is charge per unit time. Multiply current times time, and you get charge. That's what your batteries are doing. This is using up the charge like crazy, having to provide charge to that one, to that one, and to that one, whereas the other one, same charge through all three. Dimmer lights, but the battery lasts a lot longer. Okay. And here's the crazy part. Okay? If all those had the same resistance on them, you add another one, what's the overall resistance of the circuit? Increasing or decreasing?
Decreasing.
No, it's decreasing. You're right the first time. Because you got the same voltage here. That hasn't changed. You're having to provide more current. So more current, same voltage, that means your overall resistance is decreasing. And that's problematic, okay? Because you put more things on the circuit, and more things on the circuit, and more things on the circuit, you can add up the current, and the current is what produces heat. The current can cause fires, okay? I can remember the first house we moved to when we were renting a house when we moved to Birmingham. My wife was starting grad school at UAB, and I was just finding work anywhere I could. And this old house, neat-looking old house, it was leaky as a sieve, but they had updated the kitchen and put lots of extra plugs in the kitchen. All the bedrooms had, and the dining room, the living room, every room had one plug each. But they had updated the kitchen, and it had plugs all over it, okay? Refrigerator, the microwave, everything had plugs. Of course, they didn't update the circuit. They just put more things on the circuit. They were all in parallel.
Never a good idea.
Never a good idea. And what you did, if you ran too many things, and it had an old, not a circuit breaker, but a fuse box.
Oh,
And so if you had, generally if you had two appliances or three appliances that came on at the same time, pop, there goes your fuse. We kept Big B in business. That was a drugstore close to where we lived back then, by buying fuses. We bought them in gross, because, yeah.
Is that what you call a short circuit when a power is cut off by too much power? I mean, the wire is cut off by too much power.
Okay, yeah. A short circuit will do that. You're absolutely right. Because then, and that was in the lab that we did, you probably just turned it in, when you had the straight wire, you had a resistor, a light bulb here and a straight wire there. The current is like students. They follow the path of least resistance, okay? It won't go through the light bulb because there's more resistance there. It goes this way, and it'll get hotter and hotter and hotter, and that is called a short circuit. And open circuit is where you have a break in it. The light goes off both ways, but it's for totally different reasons, okay? So here the overall resistance drops as more elements are added because you're providing more current to each element. The total circuit current increases as more elements are added. Here is the formula, and this one's much harder to do than series resistors. Oh, and it's in the way. There it is, okay? It's a reciprocal relationship. 1 over your total resistance or effective resistance is 1 over R1 plus 1 over R2 plus 1 over R3. The more you add here, the smaller this becomes. It is incredibly counterintuitive, okay? Your overall resistance gets less and less the more you add, which means you get more current, and therefore you can have more likely to have a fire or overheat, or hopefully your circuit breaker breaks, okay? Now, speaking of Christmas lights, we put up in our backyard a small greenhouse. It's not a big major greenhouse. So because we wanted to keep some plants over winter, but we didn't have room inside for all of them. So we put up a small greenhouse, and it's not really all that great of a greenhouse, so it wouldn't keep them hot over, like we're going to have a couple 20-degree nights coming up this week, and it would not keep the plants from freezing overnight. If it's more than an hour or two of sub-freezing, they'll freeze. So my wife read this somewhere, the old Christmas lights, now not the ones that are in series, but the old lights that would get so hot and they were afraid, they burn down trees.
The ones that have the bigger bulbs?
The bigger bulbs, yeah. They would say, no one uses them anymore. So we searched around in our families and stuff like this. You have any of these old things? We run those Christmas lights through the greenhouse, and that produces heat because that's why, we don't have anything that can burn down, and that keeps the greenhouse warm. And it looks really neat too, all these Christmas lights in there. But when I tried to string too many of them together, pop goes the fuses. Because each string has a fuse in it. You get too much current going through there because they're in parallel. Okay? And that's exactly what's happening there. So I can only run 3 strands in there. Even though I got several strands of lights, only 3 will go without popping a fuse. Okay. Let's look at household circuits now. This is, let's just do a few figures here. Figure 6.34 shows a generating plant. It looks like a hydroelectric plant. Boy, look at the size of those transformers. Those are step-up transformers, high voltage, low current, so you can send that power for a long distance. Whereas on the right, that smaller transformer, we saw a picture of that, that's a step down right outside your house or apartment or whatever. There's a Science versus Society, and Society. Back in August 2003, I bet you that was before some of you were born or you were too young to remember it, right? They had a very major blackout in much of the northeastern part of the U.S. New York, Ohio, just huge areas, Pennsylvania, total blackout. And there's a little blurb on that with a few questions. It's pretty interesting to read. Okay? Now, before we get to household circuits, let's do examples 611 and 612. Okay? 611. 3 resistors with a resistance of 12 ohms, 8 ohms, and 24 ohms are in a series circuit with a 12-volt battery. So here's your 12-volt battery. I'll draw it this way. Okay, I'll just do it that way. And here we have a 12-ohm resistor. Here we have a 8-ohm resistor. And here we have a 24-ohm resistor. Going back into the battery here. Okay? What is the total resistance of those 3 resistors? Someone already answered it. What was it? 44. You're absolutely right. Our total is 44 ohms. Okay? That's the answer to the A part. The B part, how much current can move through that circuit? They told us this was a 12-volt battery. How much current can go through the circuit? I'm going to draw a conventional current here. Say again? I is equal to 12 divided by 24, which would be 12 divided by 24? Point what?
12 divided by 44.
Oh, 44. I'm sorry. I thought I put 24 down. Okay, you're absolutely right. I thought, where did that come from? Okay. 44. Okay. And what did you say that was? 27 what? I can't hear it. 27 amps. Okay, got it. Okay. My hearing's bad. I thought you were saying another digit. Okay, 0.27 amps. Okay? That's the answer to the B part. The C part says what is the current through each resistor? Exactly, because the same current goes through every one of them. So the A part was this, the B part was that, the C part was also 0.27. Now, what's different here is what's the voltage drop across each one. That would be 12 ohms times 0.27. That would be the voltage drop here. 8 ohms times 0.27 would be the voltage drop here. 24 ohms times 0.27 would be the voltage drop here. And that would add up to 12 volts. Okay. Good deal. Y'all did that really nicely. Okay. Now, before I get to the next one, let me just make a point here. The whole page on page 168 is solar cells. And they're using these more and more for a variety of things. And the solar cell, and this describes it, well worth a read here, especially if you're wanting to see how these things are going to be coming into the future, and they're here. Have any of you been in downtown Birmingham much? You notice the bikes they have up in various places? Okay, those bikes, some of those have little assist on them. Those are charged by, and if you'll notice all those stations where they park the bikes, there's a solar cell panel above them, facing south, and those are charging the bikes through solar, not through any electrical that's not tied into the grid. Those are providing. Huh? Okay, yeah, some of the bikes have little electrical motors in them to help you go up and down hills, uphills better. Pretty lazy, right? But my wife says, I want to ride those. Okay.
Those are some grading bikes?
Yeah.
Yeah, right.
I've never do that.
Yeah, not all of them have those. The ones with a little zag line somewhere on the fender, those are the ones that have the assist. But they have the power there, and they're all done by that. Okay, so that's worth a read. How in the world those solar cells work. Nice little blurb. All right, let's clear that out of the way. And let's do example 612. Assume the three resistors in example 611 are now connected in parallel. So we have, again, our 12-volt battery. This is 12 volts. And this time it's connected to a, what was this one, 12 volts? 12 ohms, yeah, 12 ohms. This one was 8 ohms, wasn't it? And this one was 24 ohms. Okay? Now they're connected in parallel, right? Let's answer sort of the same three questions. The first one's a lot harder to calculate. What is the combined resistance of these? What's the formula for this if they're in, the resistors are in parallel?
R total.
1 over R total is equal to
R1.
1 over 12 plus 1 over 8 plus 1 over 24. What have you got to do to get that to work?
Common denominator.
Common denominator, what would it be? 24. Okay. How many 24ths is 12? Is 1/12?
2.
That's 2 24ths. How many would be 1/8?
3.
That would be 3 24ths. So add those together. 2 plus 3 plus 1 is 6 24ths. So this is 6 over 24, which is reduced to 1 over 4. So what's the total resistor? No, you flick it. You know, yeah, it's 4. So R total would be 4 ohms. Here is the amazing thing. That's a 12 ohm resistor here, 8 ohm resistor here, 24 ohm resistor here. What's the total resistance of that whole circuit? 4 ohms. Less than any of those. Less than the least of those. 4 ohm resistor. And you keep adding more, the resistance drops. Amazing. But that's because your current is having to increase with the same voltage down here. So your total resistance is 4 ohms. The beef thing says, what is the current in the overall circuit? Current in the overall circuit. How would you get that? Okay, I total is equal to V total divided by R total. So that would be 12 volts divided by 4 ohms. That would be 3 amps. Very good. So you get 3 amps through there. What was on the previous one when it was in series? 0.27, less than a quarter. I mean, a little over a quarter. This is 3 amps. A lot more current involved. Okay? What is the current through each resistance? Well, you have 12 volts here, 12 ohms there. What current has to go through that? 1. 1 amp goes here. How about here? 1.5. How about up here? 0.5. These are all amps. What do those happen to add to? It adds to 2 plus 1 is 3. There's 3 amps right there. Okay? Add the amps to the other. You got to get it. Very good. Y'all got it. 1 amp, half amps, and half an amp. Okay. All right. Now we're doing household circuits. I think this is the last section in here. Okay. Now, most of the house is done in parallel. Okay. Otherwise, sometimes things aren't done too well in parallel, but they are. But you always have some things in series. For instance, these lights. Are these lights in parallel or series? Parallel, because you take out one bulb, the others keep running, right? Okay? But what is in series with these lights? The switch. Because you turn on the switch, they all come on, or turn off the switch, they all go off. That's in series with it. So you have some things in series and some in parallel. That's why they say a combination of series and parallel circuits. The light fixtures in the room are parallel, but the switch has to be in series with those. Okay? Now, on the Birmingham campus and the office I use there, I don't know who wired that thing, but there is a receptacle on this wall, and one on this wall, and one on that wall. Okay? And the one on this wall, you turn on or off the light switch, that receptacle goes off too. Whoever did that, wacko, okay? They did not do a good job of wiring. The other two are in parallel with it, but that one's in series with the switch. With the light switch, that's not good, okay? Not going to hurt anything, but you think you're charging something or you're using your computer, you realize the light's off, you're running down your battery. Okay, your appliances are usually in parallel, okay? Remember I mentioned the kitchen in the old house, that first house we lived in? If the compressor on the refrigerator came on while you had the coffee pot on, pop goes the fuse, okay? Just would not handle it. So you had to be very careful. You could not run the toaster and the microwave at the same time. Otherwise the microwave would go, it was really bad, okay? And pop goes the weasel, okay? The circuit breakers or fuses prevent the overloads. Thank goodness. Otherwise, get too hot, catch on fire. Okay? So here we have this light is connected to this switch. Okay? But this receptacle is not on the switch. So the light goes on and off with the switch, but because this is a parallel circuit, it's series with the light bulb, parallel with the receptacle. Another receptacle, another receptacle, another receptacle, and every one you add. The toaster, lots of current. The can opener, not that much current. The radio, not that much current. But if then you have your compressor and your refrigerator on the same circuit, the oven on the same circuit, you know, after a while, pop goes the circuit breaker. Okay? So, and this is showing the circuit breaker here. Now, in our garage, we have a circuit breaker that has gone out. And I don't quite feel qualified to change that because, number one, that box out there, I don't see where the power to the box is. So I'm a little hesitant to change that. But my younger brother works with electrical stuff. If I can ever get him to come over to the house, we'll change that out. I probably could do it, but I'm just a little hesitant. And my wife doesn't think the insurance money is worth it, so she doesn't want me doing it either. So anyway, be careful around this kind of stuff. Okay, now, other things about your household safety. All the plugs in this room are 3-prong. Very good. Not all plugs are 3-prong. Okay? What you usually have is a potential difference between 2 wires in a device. That's what's doing it. One of the wires is the energized load carrier. Now this is an AC circuit. The other is your ground wire or your neutral wire. Okay? If you notice most of your plugs, now this is a 3-prong plug, but even if it wasn't, the newer plugs, and when I say newer, this is in the last few decades, but many years ago, in fact, that old house I was talking about, they didn't have it. It didn't have, you never could tell which one was the load. Those wires were exactly the same. But more modern things, one plug is bigger and one smaller. Which of those is energized? Which is the load? And which is the ground?
The smaller one
Is the load.
Yes.
You would think it would be the other way around, but it isn't. The big one is the ground, and the small one is the hot prong. But some things, for instance, this isn't going to damage my computer. It doesn't matter. These two are exactly the same because it's going through a converter anyway. So it doesn't matter. It doesn't care which way it's going. It's going to be fine. However, the HP that I had, remember about midway through the term when my computer died, the HP, it mattered, okay? HP, I think, is a little better, more quality control than Fujitsu. Okay. All right. So one side is the energized load carrier, the other is the grounded or the neutral wire. Now, this plug has a 3-prong plug that provides another grounding wire. Not just this one, but then this one as well, okay? And that gives you a little more protection. But you can have other things, and this is a polarized plug here, like I said, but you can also have another level of protection, and that's a ground fault interrupt. Where do you usually find these?
Bathrooms.
Bathrooms and kitchens. Anywhere you have water nearby, that your ground fault interrupt, because if something, an appliance like a hairdryer or something like, would fall into the tub or the sink when you were using it, that ground fault interrupt, as soon as too much current through there, it breaks the circuit. Now I can remember the old mystery things on television. This is way back, long before your time. A real popular way to bump off a spouse or somebody like that was if they were in the tub, drop the radio in. You know, they're fine. You know, ground fault interrupt would keep that from happening. Okay, but back then they didn't have ground fault interrupt. Now I mentioned my younger brother worked for an electric power company. Okay, a small rural one. He hates GFIs, and he goes through, once they put them in his house, he goes in and takes them out. I don't think that's a good idea, but he's a hard person to argue with. His mind is like a steel trap, but it's just closed. No, I'm just kidding. Never mind. All right, that was it. I shouldn't have said that about my brother. That was the last slide. Okay. Any questions? Chapter 6, Electricity and Magnetism, covering a lot of ground and grounds. Okay. 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 Yes.
So
Somebody was listening. Amazing. Okay. Now, I say this every chapter. I'll say it again. Nothing replaces reading the chapter. If you haven't read it yet, hopefully you were reading it before we got to the stuff. But if you haven't, please read it before Thursday, which is test day on chapter 6. Okay? Bring your formula and equation sheet, anything you want to write down on a piece of paper for the test. Last 30 minutes on Thursday will be that. Okay? The summary at the end of the chapter, this is a pretty long one because this was a pretty long chapter. So there's quite a bit in the summary here. That's well worth a read as well. Yes? Say that one more time. Are we learning anything? Are we learning anything? Of course, you're coming to learn anything. I didn't ask that question. Okay. We're covering the material on Thursday.
So we're going to do it at 8.
Okay? Chapter 8 is Thursday. In fact, we'll start chapter 8 today. We won't get very far, but we'll start chapter 8 today. And most of Thursday, the first 2 hours on Thursday, well, it depends. If we finish the chapter in 2 hours, then we'll have a lab the next 2 hours, and then the test the last 30 minutes. I doubt if we're going to finish chapter 8 in 2 hours. So 4 hours of lecture and that. Then we'll do the test on chapter 6, and then on Tuesday we'll have the lab. And then if you want to take the final, you can. That's perfectly fine. You don't have to. The final is scheduled for Thursday of next week. I know. Most of you, I think, will, but you don't have to. Okay. I know. I understand. That's why I offer it that way. Okay, so there's your summary. You have a summary of equations. 11 equations in this chapter. Okay, quite a few. Be ready to be able to use any one of them. Okay? Key terms. There's a fair number, about average, I guess, but fewer than 11 is a lot of equations. Key terms, you don't have that many. Applying the concepts, 50 questions, which is probably a little more than normal. Multiple choice. These will be most similar, not the same, but most similar to most of your questions on your test. If you know those 50 questions, get the answers right on the vast majority of those, you're probably in really good shape for your test. Questions for thought, 12 of those. That's probably a few fewer than normal. For further analysis, we got 7, which may be a few more than normal. There's a little invitation to inquiry, earth power. Pretty nice blurb to read. The parallel exercises here probably are going to be pretty good for you to look at because you will have at least, I'm trying to remember now, I think maybe, I know at least 2 and maybe 4 actually calculation problems on the test. Okay, they're not going to be really difficult ones, but you will have a few that will be calculations. Most of them will be multiple choice, but a few will be calculations. So, worth your time. Parallel Group A exercises, those have the answers in the back. If you have the big books, the Group B don't have the answers in the back. So that, again, is something worth looking at. I wish we had time to do Chapter 7. That's light. It's a really great chapter, but we don't have time to do it. We need to get a little bit into chemistry. So any questions on Chapter 6 before we end Chapter 6? All right. So let's, oops, yuck, quit that, okay, quit that, quit it, okay, all right. All right. All right, Chapter 8. This is the first part of the chemistry section. It's the only part we're going to be able to do. I'd really prefer to do some of the bigger chapters, later chapters in chemistry, but you have to have this fundamental stuff first, so we're stuck here. But it's good stuff. And a lot of it's stuff we've done already, too. Let me get the slideshow set up from current slide. All right, we're talking about, in Chapter 8, atoms and periodic properties. And again, we saw atoms at the beginning of chapter 6. You've seen atoms. We talked about atoms in previous chapters, especially the heat and temperature. There's been atoms talked about a lot. This time we're going into a bit more, especially with these periodic properties. Okay? Neat looking figure there. I don't know what it's really representing. You have another neat looking figure in your book. I don't know what it's representing either. But let's go on to the core concept, which is on your leading page. Different fields of study contributed to the development of the model of an atom. That's a pretty lame core concept in my mind, but it's certainly true. Physics was involved, chemistry was involved, lots of different areas, fields of studies contributed to the development of the model of an atom. Mostly physics and chemistry. And I'd say physics may have led the way in many senses. So the atomic structure was discovered, and we've hit this before. The ancient Greeks, this is long before Aristotle even, Democritus, 460 to 362 BC. He had that. Again, the Greeks just did thought experiments. They thought through things. He said, what if you have a piece of material here, break it into two pieces, and then break that into two, and just keep breaking, breaking, and breaking, and breaking, and breaking, and breaking, and finally, can you get to a place that, yes?
I'm sorry, continue.
Yeah, that you can't break any further. You get the smallest piece of that material you can have. He called that indivisible, and the name in Greek was atom. That's where we get the name atom. Okay?
I was going to ask, isn't this the same thing about, the story about the boy in the checkerboard and the putting the rice and doubling each thing?
Yeah, that was illustrating exponential growth. Yeah, I used that in the last class. Yeah, I don't know that we're going to run into that one here, but that's getting bigger. This is getting smaller. Okay, so same type of thing. Okay, now Democritus came up with that idea. There is some smallest piece of matter that you can have. You can't get any smaller. He called that the atom, the indivisible piece, atom. But along came Plato and Aristotle, and they said, "Nah, we don't believe that." Democritus was long dead. They said, "Nah, he had it wrong." They said matter is continuously and infinitely divisible. It's a continuum. You can't get to the smallest piece. They were wrong. He was right. Okay? Along came a British scientist and engineer, John Dalton, in the early 1800s. This is AD, not BC. So this was 1,200 years later. Reintroduced the atomic theory to explain chemical reactions. Now, you might say, how do we come full circle here? Well, here's the deal. People believed Aristotle. Everybody believed Aristotle. He was such a great thinker, he must know what he's talking about. He had this thing, remember what his four elements were?
Earth, wind, and fire.
And water. Okay, earth, wind, water, and fire. Okay, you like to sing music. Okay. So, that was the four elements. Well, people said, hey, earth is cheap, air is cheap, wind is, fire is cheap, water is cheap. We can use these cheap materials. If that's all there is, we can combine these in different ways and get gold. We can make a fortune, or platinum, or silver, We can take really cheap materials and put them together in different ways to get a really valuable material, okay? So they started doing this and trying to, and boy, there's so many different ways you could put them together in so many different combinations, more heat, less heat, varying things. So they had to start keeping very careful records to keep from reproducing and doing something over and over again. And so they could communicate with each other as well and try to beat the other guy. And so that became the group of people called the alchemists. Okay? They were trying to come up with finding gold or some valuable things from cheap materials, and later they became the chemists. Well, they kept these careful records and were doing all this, and in those careful records, John Dalton recognized that when you had certain quantities of matter and combined them together, they always went together by what they called the ratio of definite proportions. If you had so much carbon and so much oxygen, you could combine them together to form carbon dioxide. If you had extra carbon, you had carbon left over, extra oxygen, you had oxygen left over, but they always combined by definite ratios. That was Dalton's thing. So he said, look, if they're doing by definite ratios, there must be some smallest piece. Those are combining in a ratio. And he was absolutely right. So he came back around to the idea of atoms that way. Now that's a representation of an atom. I don't know if you can see it very well from where you're sitting, but this is the nucleus, way bigger than any nucleus will ever be, but they made it bigger so you can see. These are made up of protons and neutrons, okay? Protons are positively charged, neutrons have no charge. Surrounded here by electrons. Now it looks like a lot of electrons, but there really aren't. Those are just all the different places those electrons could be. You have a shell of electrons here, and then another shell out here. We'll be talking about that later. Now this is three-dimensional, because some of these are on this side, some are on the back side there, but these are just places where the electrons could be. To be a neutral atom, you have the same number of electrons as you do protons. Neutrons don't matter, okay? Same number of electrons as protons. Protons are much more massive, but electrons take up much more space. They're not bigger, they just fly around through space, whereas protons and neutrons really jam together in the nucleus. Okay, I'm afraid we're going to have to probably stop there. Sorry about this, and we'll pick up next time with Dalton's atomic theory. Okay, and that begins at the bottom of page 206, and we'll go from there. Okay? So, let's pause this. Okay. Here we have an electromagnetism board, thanks to the Toyota program. Right. And on this, you'll see there's a couple of horseshoe magnets with some magnets up here. And I'm going to pass out to you some pieces of metal. Okay? Don't do anything with them yet. Okay. Now, what we're going to do is check to see if these pieces of metal are magnetic. So, on either one of these things, no, it's on the side. Okay. Is that magnetic? Aluminum. Aluminum. No. Copper is a real good conductor. Is that magnetic? No. Iron. Who has iron? Sort of a rusty looking thing. Yep, you got it. Come see. Maybe these aren't magnets after all. I don't know. Okay. Let's see. Hold it against the side of one of those. Against the side. Yeah. Oh, look at there. Yeah, iron is magnetized. Who has lead in their pants? Okay. No, you don't. I think you do. PB. Okay. Try lead. Put it against one of the sides here. I don't care what side here. Magnetic? Nope. Lead's not. Nickel, sort of a shiny one. Okay, yeah, let's try nickel. What do you think? Oh! Yeah. Okay, how about zinc? Who has zinc? You do? Okay, try it. Yeah, no. No. Okay, very good. We don't worry with plastic, wood, and styrofoam. The only reason I put styrofoam on there, sometimes styrofoam pieces stick together and you might think they're magnetic, they're not. So I quit doing that. Okay, so if y'all who have those, I need them back. What's that? SN was 10. Who had 10? Did someone do 10?
I had 9.
No. SN. Oh, you had 10. Okay. So 10 was another. Who had zinc? You have zinc. Okay. Yeah. I'm sorry. Try zinc.
What was the AL?
AL was aluminum. That was another.
What about the
Ni, what do you had Ni, didn't you? Yes, it was. And besides, anyone recall what were our three naturally occurring magnetic materials?
Nickel, cobalt,
Iron. And we didn't have any cobalt, but we had iron and nickel, and they both were. All right.
So we had no cobalt's gonna
We
be
didn't have cobalt. No.
What's CU is
Cu was copper. So I'm missing one, folks.
right there on top of the book bag.
Right. Oh, I see. Okay. Let me put these away so I don't lose these. I use them for other labs as well. Okay. Yeah. Hang on to that for a moment. Okay. Now, what we have is some iron filings, so be careful with these. I don't want these spilled anywhere. Okay.
I think they taste good.
Okay. You said they taste good?
Yeah.
Okay. Now, it says test. Several pins have been placed through pieces of styrofoam. Somewhere in my pocket I have one. And the only reason I did this is in the old days I floated these in a glass of water to make a compass out of it. I don't need to do that because I've got a compass now. But here's a pin. Just place through that so I can easier to keep up with it and not lose it. And it says, see if it is magnetized by touching its point into the container with the iron filings. Who hasn't done something yet? Who didn't have one of those strips? Okay. Stick the point into the iron filings and see if it's magnetic. Oh yeah. Okay, so the point was, okay, wipe those off. How about flipping it over and trying the head? If maybe that's magnetic too. Let's see. Oh yes, okay. So both of them are. All right. If it is magnetized, now I'm not going to put it in a thing of water, but here we have a compass needle. Okay? This compass needle is pointing pretty much, the trouble is all these magnets around, pretty much to the north. So hold it so it's to the north. And what we want to find out is which end, the point or the head, is the north or south seeking pole. How can you tell that? With your pin that's there. How can you tell? We found they were magnetic. How can you tell which is north and which is south seeking? Say again? Okay, start with the point. Okay, that's the head. What does it do when you put, oh, what is it doing? It's chasing it around, or is it drawing? It's pushing it away. So what must be the head? Pushing away
south.
Really? North, because like poles repel each other. Test it with the south and see what it does. The south. Yeah, it chases the south. So that must be, the head must be a north seeking. Flip it over and see about the point. Whoa, it drags that north seeking. So that must be, the point must be south seeking. Try it on the south pole of the oh, it chases that thing, doesn't it? Okay, so that the point is south seeking. Really? Let's try it again. Yeah, south seeking. You're absolutely right. The point is south seeking. All right. Now, I went through all the pins I could find, and I came up with one that was the least magnetized of all. So who hasn't done something yet? Okay. Why don't you take that and dip it into the iron filings and see if it's magnetic. Okay, as much as the other one was? No. Okay. How about the head? That was the point. So wipe those off. Okay, and try the head, see if it's more magnetized or not. No, not much at all. Okay? So that is a weakly magnetized piece of pin. Okay? Now, what I want you to do is stroke it on the edge of one of these magnets. Okay? Yeah. And you want to do the point or the head? Oh my goodness. She made it a lot more magnetic. But she struck the head. Okay, did you increase magnetism? Okay, let's flip it over and do the point. Yeah, no. Just stick it in. What do you think? Should it be?
Yes.
Is that more magnetic than it was?
Yes.
Now, how did she make the point more magnetic if she only struck the head? Okay, because magnets are always
Yes.
dipolar. Bipolar means they have something. Okay, all right. Yeah. Okay. Means the same. Twofold. Magnets are always, so even though she only made stroke one end, she made both ends. Much more magnetic. Okay, what we need to do is determine, do we know which is north and which is south? No. Do we know which of these is north and south? They both. We have to use the compass. So, okay, first, wait, before we do that, let's do number 3. Okay, number 2 was, now touch the head onto the filing. Did you increase the magnetism of the point as well? Yes. Okay, number 3. If yes, explain how you increased. Oh, we just did. Okay, y'all write it down.
Magnets are dipoles.
Magnets are always dipoles. So if you increase one, you've got to increase the other. Okay. Now, dipoles. Yeah. Magnets are always dipoles. Just because she stroked only one, the head on the magnet, she magnetizes the point as well, because if you increase one, you increase the other every time. Okay, so using the pen and the compass, let's figure out which is north-seeking of that pen. What would you say?
That's north-seeking.
Okay, the point is north-seeking. Let's check the other. Okay. Okay. The head is
South.
okay. What is it doing? Yeah, it's pulling the so it's south-seeking. So the head is south-seeking. Now, what we've got to do now is head down to the, what's that? No, we're not going to 265. There's no filing cabinet in there anymore. It's wood now. So what we're going to do is take our compass. Okay, who hasn't done it? I'll take this. Okay, where's the other one? Okay, throw it in the water. See if I can. Okay, let's go down to the area around the records office. Okay, we're going to be coming back here real soon. We're just going for a brief time down here. Okay. Someone's got the compass, right?
Yes.
Someone have the compass?
Yes, sir.
Okay, good. Read the compass.
Hey, cool, his brains popped out.
appropriate. I mean, he's serious.
They're really slow.
Yeah.
It looks so sporty.
Well, if you-
Most of the Del Sol sold in America were SIs, and and all the SIs were B16s.
Wait, what?
Yeah,
I made it B16 also.
all the SIs were.
Never mind.
And then you had the Del Sol VTEC, which was the B16 that had around it. Okay, so are most other Hondas.
Okay, who did we wind up losing?
They might have left.
Okay, we still got Rachel, we still got John, we still got Yale, right? Yeah. Did he make it back? Yeah, I see you. Okay.
I believe we lost to Jared.
J-Rod, Andrew,
I bet you David, right?
And David.
We lost
Jared,
there
Andrew, and
too.
David.
And who was the other one? You named one more.
Jared,
Jared?
Andrew,
Oh, Andrew. We lost Andrew. Okay.
and David.
And David. Okay. All right. Now, let's make our way here to the Toyota system here. All right. And we're going to have to do some. What's that?
Yeah.
Okay, yeah. We're going to fill it back. All right. Wait, otherwise they'll get discombobulated. Oh, I forgot to take my computer down there. Oh, shucks, those folks that weren't here won't be able to hear what we did. So sorry. Okay.
National tragedy, somebody called Trump.
I'm sure they can find a filing cabinet at another school. With the
Hit it with a hammer.
and they'll get it solved.
All right. What we're going to do here. That's spill either. Okay. I haven't done it in this lab before. I thought it would be more space here that we can. So we're going to do the black here, the black here, and we're going to start here. And I'll go red here. All right, everybody come so you can see what's going on here. Oh, I need the compass.
My dad fixed some of the cards.
All right, now this is a little, okay, got it basically pointing north. There's so many magnets here, it can be problematic here, so let's try and balance it somewhere up here. Okay, that's not bad. Okay? Everybody watch what we're doing? At the Toyota Electromagnetism Master Station A, there we are at Station A, wire the black wire to the black socket, here and here, and the red wire to the red socket, there and there. Okay? Place a compass near the coil, we've done that. And what we're wanting to do, let's see. Let's try that. Yeah, not too much. Somewhere right about there. Let's see if this will give us do what we need. Okay? It says touch it to the positive end of a 1.5 volt battery. Not going to mess with those. The batteries run out so fast, they discharge so quickly. I'm using this. So we'll do more than 1.5 if we need to. I'm going to start, well, I'll let somebody turn this and see if we get any deflection of the compass needle. So So turn this up, crank it up slowly. Crank it up slowly. See if you get any deflection on the compass needle. Keep cranking, keep cranking, keep cranking, keep cranking. Do you see it? What is it moving?
Towards the west.
Okay, so the south-seeking pole of the compass is moving away from the left end of the coil. Is that right?
Can we just say the north is moving towards it?
You could say the north is moving towards the left end. You got to get a direction of that. Okay. All right. And then when I turn the pipe juice off, it went back where it was. However you want to call that, you saw it. Either the south-seeking pole of the magnet moves away from the left end of the coil, or the north-seeking end of the magnet is moving toward the left end of the coil. Okay? Whichever way you want to do it. Okay? That's what happens in the compass needle. So which is the north pole of the coil? The left or the right?
The left.
The left.
The north was attracted to it.
So therefore it's...
Oh, it's right.
Okay, good. Okay. Everybody agree?
Yes.
Okay.
I don't agree with that.
What's that? All right. This time I'm going to touch the red wire to the negative end. So I'm going to swap my wires here. Okay. And so I'm going to crank it up again.
No, all the way up.
Keep cranking. Turn it, turn it, turn it. Turn it.
So now it's going to.
Now it's drawing the south-seeking pole toward the left end. Okay? Turn it off, it went back. Okay? Are there any changes? Yes. Yes. It was reversed. So, it's not just the moving charge through a wire, it's which way it's moving. Okay? And when you do it one way, it makes one end, or the other way, it makes the other end. All right, let's move to station B. Okay? Red to red, black to black. This back, red to red, and black to black. Work. All right, this time we're going to connect yellow to yellow. All right. Now, what is that connected to over there? Can you read that? Okay, that's an ammeter measuring current. Okay, do you see any power supplies or anything in here?
Power supplies, yeah.
Okay, yeah, they're connected, but there's no juice going to it now. But it's connected to this side. Is there any power supply on this side?
No.
No. So, do you expect to see any current flowing through this side?
Now? Like right now?
Not. Okay, right now there's not. It's not moving. But what happens if we...
You're going to get current flow.
Why?
Because there's going to be current flowing.
No, the current's going to be flowing here. It's not going to be flowing there. This is only going to supply this coil here.
Okay. Well, then you have all the answers.
Okay. All right. Now, what we're going to do, and this is going to take some coordination here, folks. And it's going to take a little bit of effort, and it's going to be weird, a little bit weird, okay? Because what we have to do, I want one person looking at these lights. These are LEDs, red and green, green and red, okay? Another person is going to be looking at the ammeter, okay? And the other person is going to be, that'll probably be me, is going to disconnect and connect. Okay, I'll call out which I'm doing. Okay? So when I do that, then the people who are looking at the lights and the people looking at the ammeter are going to need to tell us what's happening. The trouble is you can't see the lights with the lights on. So we're going to have to do this first with the lights off, looking at the lights, then we're going to turn the lights on and look at the ammeter. Okay? It's a little bizarre.
We do have a flashlight. You could just put it on that.
You could, if someone has a flashlight, that would be fine too. You got it? Okay. So you can look at that. Just don't shine it over here where it messes up. Okay?
Okay.
Someone one that's going to need to. Yeah, but let's see if we get. I'm going to play with this a little bit. It says do it with a 9-volt battery, so I'm going to crank this up to 9. It may or may not be enough, but nothing's happening, is it? Even though I'm cranking this up to 7, 8. Oh, okay, that's fine. Okay. Now, did you see anything happen with the disconnecting? Okay. Connect. Disconnect. Did you see anything happen? Yay or no? Did it move?
Yes.
Okay. But it didn't when I left it plugged in, did I? But when I disconnected, it moved. Okay? The ammeter. Okay? So, ready on the light? Okay? Oh, man. Okay. This is for the LED lights. Okay? Ready? Turn off the light. Connect. Disconnect.
When you connected first, it went red.
Okay. All right. Turn on the light. When you connected, it went red. When you disconnected, it went green.
Yes.
That's at station B. This is number 4, C4. That's an explosive, by the way. Okay. Okay. One person. Okay. The
Connected, it went red.
connected, it went red. Disconnected, it went green. Is that what you said? I wasn't looking. Is that what you said? Okay. Now we are on that same number 4. We're going to have to look at the ammeter. Were you able to do it with your light on? Were you looking at the ammeter when I did it before? What did it do? Can you tell? Okay, well, let's do it now with the light on. Okay, I'm going to connect, and you tell me what the ammeter does. You ready? Connect. Move what? Which way? Positive. Okay, disconnect. What did it do? It went negative. Okay, so that also goes on line 4. What happens to the light and the ammeter? And that was only on connecting, by the way. So don't put disconnect yet, just on connecting. Connect, what was it?
It went red.
Red, and the ammeter went positive. Okay, number 5, when the wires are disconnected, what do lights and ammeter do?
Light went green.
Light went green.
Ammeter went negative.
And the ammeter went negative. Very good. Okay, this time I'm going to switch my polarity and drop my plug. Okay. Okay. So we're going to turn off the light. When? Okay. Connect. Disconnect. Okay. All right. Turn on the light. Okay. Hold the negative. What happens to the lights and ammeter? Only do the connecting part here. What happened on connecting? You said green? Green. Okay. Look at the ammeter. Ready? Connect. Negative. Disconnect. Positive. Okay. Oh! Okay. That was something on the order of 9 to 15 volts, by the way. Did the ammeter move much? No. Very little. Okay. Very. Okay. That was number 6, right? And number 7. 7 was disconnect. Y'all got that? Everybody got 7 disconnect? Wait.
Disconnect with
Red.
Red and ammeter went positive. Okay? Now, what we're going to do now is try to explain the observations. Oh, yeah. This is the fun part. Okay. Why, when I have it plugged in, is the light not on and the ammeter not moving at all? But on connecting or disconnect, that's when you see the lights come on and the ammeter move.
So nothing happens when it's connected, but it happens when it's disconnected.
Oh, something happened on connection and disconnect.
He's talking about
the magnetic field was still flowing through there.
What's that now?
The magnetic field was still.
Okay. Okay,
Yeah.
you're
When
very
you-
close. good.
When the coil is energized and de-energized, a magnetic field is created.
And why?
Good question.
Because you have a changing current. It's going from 0 to whatever, or whatever to 0. It's only a changing current that induces a magnetic field. That's it, exactly. Changing current induces
It's the
a
same way
magnetic
a
field.
relay works.
Yeah, okay.
So we can just put changing in current.
Okay. Only with a changing current do you get an induced magnetic. Right. Okay. Let's say so then. Changing magnetic field do you get a current? Because we were measuring current. The light indicated current, the ammeter indicated current. So only the changing magnetic field induced the current. That's electromagnetic induction. All right. Okay. Just the fact you had a magnetic field doesn't make current. Okay. Now we're going to station C. Okay. That's in Spanish. Okay. All right. Red to red, black to black. Reverse these again. And move my yellows to yellows. Okay. Team effort here. Okay.
Teamwork makes the dream work.
All right. Trying to find where we are now. Oh, at station C, number 9, place the colored wires, corresponding plugs, moving the yellow wire, blah, blah, from 2 to 4 we did. Place the red wire on the positive end. I got it. Now, I'm going to crank this down. It was at 9.3, right? I'm going to crank it down to closer to 1.5 or 2. Okay. Well, I've got it at 2 now. Okay? Now, give me lights. What's that?
Adam, you keep abandoning your post.
That's why I want to plug it in. Ready? Okay. Connect.
What?
Yeah, well, I wiggled it some. Disconnect. Green. Okay. So, okay. Turn on the light. Look at the ammeter. Ready? Connect. Disconnect. Negative. Okay? Very much similar to what we had before, right? Okay, did everybody get that? No. This is number 9 at station C. Place the colored wires, corresponding plug, blah, 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 blah. Record the responses of the lights and ammeter on connecting and disconnecting. So you do them both on this one. Okay, connecting was green. Was that right? What was it?
Connecting was red.
Red. Connecting was red. And ammeter went positive, disconnecting was green, ammeter went negative, right? So you get all 4 of those down there. Now, question for you. Did the ammeter move more this time or less? More? Well, I had a lot less current. I mean, voltage.
You had less coil. You had less coil, right?
Say again?
Less coil, less copper.
Oh, you're really close to it. Look at where the
Yeah.
coil is now.
Wait.
The coil is inside the other coil.
Wait a second.
So therefore, a lot more field lines are being cut. Over here, just the edge field lines are being cut. All of them are being cut by this one. So even though you had much less voltage across there and less current, you've got a lot more field lines being cut. So therefore, you got a bigger response.
Okay, what's that for 9 and
That-
10?
Okay, that last part we didn't do. Let's do 10. We're going to switch the leads.
Yeah, not unless you wrote both connecting and disconnecting.
Okay. The 9 was just connecting, what was it, red, and ammeter positive, disconnecting green, and ammeter negative. Okay, lights. I'll switch the coils here. So this is number 10. Okay. Connect.
Green.
Disconnect.
Red.
All right. Turn on the light. Look at ammeter. Connect. Disconnect.
Positive.
Connect.
Negative.
All right. Got it. So, number 10, switch the wires, record the responses.
Green.
Connect green, ammeter negative, disconnect red, ammeter positive. ammeter on number 10, ammeter went negative on connection and positive on disconnect. Yeah. Okay. Is that what you're asking? So, second.
I was my question myself.
Okay. Number 11 says, why were the responses greater at station C than at station B, even though B had a much stronger voltage? 9 volts to B. The coil was completely inside the outer coil. So more field lines were being cut by the outer coil. More field lines being cut. That's the key. How many field lines are being cut? Okay. All right. All right. Everybody got number, what was that? 11 done. Everybody got 11? All right. Moving on to 12, we move to station F here. Okay. Place the 2 sets of yellow wires from terminal 8 to 14. 8 to 14. Okay, that's where we got. Okay. One person should turn the coil clockwise. Here's a little handle, turn it clockwise. Okay. Rapidly. Someone else look at the ammeter. Turn it rapidly. Okay. What do you see happening with the ammeter?
Jumping.
Which way?
Both ways.
Positive only, right? You tell me. It bounces, but it only goes positive.
We're creating electricity, aren't we?
Yes, we are.
Yes, it's a generator.
There's no power supply to this. What we're doing, we got a magnetic field line. Which way do the field lines go? From north to south. And you're twisting this. Here it's cutting maximum number of field lines, minimum number of field lines, maximum. And if you turn it that way, it's making slight positive pulse to the positive. Okay? Now, let's try turning the coil counterclockwise and record the ammeter response. What do we see happening? Jumping negative. Okay?
So it went to it was positive.
Yeah, when you turned it clockwise, it went positive. When you turned it counterclockwise, it went negative. It didn't go alternating. Okay, so this time, flip the 2 yellow wires. Okay, do clockwise again. What happens with the ammeter? Going negative now. Do it counterclockwise. And sure enough, it's going positive. Okay. Now, you don't have to write anything down for that. But what kind of connection does that coil have? I want you to pay attention to this thing here. Notice what you have. A split right there. Halfway around, you have another split. So when you're turning this and increasing the field lines being cut by this, you're going positive. But as soon as it goes to go negative, when you're decreasing the number of field lines, you jump across and it flips the polarity. So that's why you have a pulse positive response. What do we call that connector? Close to that.
Called the connector element.
Huh?
I'm thinking of his name. Start with a G.
See. It's got a split in it, so it's a split ring commutator.
Yeah,
That.
Yes.
Split ring commutator.
I'm thinking about the limit in the book.
Right. A split ring commutator. That's the first blank on 14. What kind of connection does it have? What is the result of that? Pulse DC current. You never had AC, you only had DC, either positive or negative. It bounced, but it never went negative. It either was all positive or all negative. Pulse DC current. Okay, let's go to G. Oh, I'm sorry, we don't finish it. My house. Okay. Now, let's pay attention to what we just did. At station L, we were turning the coil in the presence of a magnetic field. And on G, we're going to be turning a magnet with coils around it. Okay? Would that work? Here we turn the coil inside the magnetic field. Here we're turning a magnet inside the coil. So what do you reckon is going to happen?
The exact opposite. Will you create AC?
Yes, we will create AC because there is no commutator here. So someone twist that, like I was just doing. Look at the ammeter. What's happening there?
Oh, it's jumping.
Jumping which way?
Both directions.
Both directions. So that sure enough is AC, alternating current.
Oh, that's where it comes from.
Okay. So it doesn't matter what's moving, it's the relative motion. You could be moving the coil in the presence of a fixed field or moving the field in the presence of fixed coil. It doesn't matter, but this time at station G, records responses to the ammeter. It alternates positive and negative. And number 16, what difference do you see from F? Alternating current versus direct current. Perfect. Why?
Because science.
Because what?
Because science.
Because there's no split commutator.
No split ring commutator on G. You got it.
That's all the information I need to get.
Okay.
Give me your reasons.
Got all this in.
Why? There is no.
Huh?
Split ring commutator. Well, some commutator.
There is no split ring. He's just told you. Reset is always when you catch up.
All right. Any questions on this? Is it short while out?
Just like you, Drag Race.
Wow. Did you say that?
Ow.
He did.
Did
My
you hear
heart.
the line?
My heart.
Did you hear the red line?
Okay.
Thomas doesn't even make it to the next red light.
I love that.
Yeah, put it on top of the book. Well, yeah. All right, so move it down. All right, good deal. Thanks.
The great burn of 2017.
Okay.
We shot her around the world. People want to hear this for centuries. They're going to hear of it.
That's 4, right?
Where do you want me to take it? Just in the classroom?
That'll be fine.
Okay.
Okay. Good deal. All right, take care. Work all out? Excellent.
Or like the week of Thanksgiving, Lacey was like, so Angel, we're going to celebrate the genocide of Native Americans. Wow. Did you? And
Rachel, you flying all the way to
Yeah, I've got it.
It's like, let's have a celebration of our new friendship. Now let's kill each other.
See you later.
on my grade book.
Yes,
Sort of right behind the computer.
Yes.
See a pile there.
Fuck your computer.
Oh,
All right, guys.
take care. Have a good. We'll see you Thursday.